Welcome to another episode of Dominic Does DIY. Today we're going to continue looking at the op amps. This will be episode number 4. We will be actually looking at some uses, another use case for the two op amp arrangements that I've already demonstrated with the comparator and the differential amplifier. In this episode, we're actually going to take a look at the differential amplifier working together with the comparator. We're going to do this by actually looking at some current traces, and we are going to make a constant current output device going across this load, which is the inductor. In the previous video with the differential amplifier, I just had a load resistor, but in this one I've changed it up a little bit, and now we are working with an inductor. And I'm doing this because I want to be able to see the current ramp up and then stop it and then start it and stop it, things like that. So we got the inductor there instead of the load resistor. This diode is here simply as a means to allow the inductor to discharge. So when I power on, the inductor will begin to discharge. Our current through the inductor follows this formula. The rate of change is equal to volts over inductance, and our current is equal to volts over the resistance times 1 minus E to the minus RT over L. Our R is our sense resistor, our L is our load inductor, and this diode is just going to be a directional piece of the puzzle here. So this over here is our switch that I'll be turning on and off. This is just a PMOS. PMOS is just a high side switch. So over on the source, I put my 5-volt load, and I'm just going to control, for now, I'm just going to control this PMOS with a standard pulse signal, so we can kind of see what happens with the inductor as we turn this PMOS on and off. What is going to happen is when this PMOS turns on, 5 volts will be applied to the inductor and sense resistor. The inductor will begin to charge via this formula. When the pulse turns off, the switch will become disconnected, and then this inductor, because we know that current can't change instantly on an inductor, current will continue to flow in this direction. It'll go through the ground, come back up the ground, and then through the diode. So the diode is our return path for when the switch is closed, for the current from the inductor to flow and self-discharge itself. If that inductor isn't there, we would see a really high voltage spike coming up on the inductor. So let's just run this and see what we got. So in our simulation profile, I'm just running it for 1 second. I've also checked this start external DC supply voltage is at 0 volts. I've checked that one for this episode. It is so that all these voltage sources start at 0, and then they will have the voltage applied after the T0 marker, so that everything will start basically off and then be turned on simultaneously. And our pulse, we're going to go just from 0 to 5 volts because the PMOS as a high side switch, our VGS has to be greater than the VGS threshold of the PMOS. It's a 5-volt system, so if we apply 5 volts, it'll turn off because I'll have 5 volts between VGS, so VGS will be equal to 0. And if I go to 0, it'll be on because my VGS will absolutely be greater than the VGS threshold of this PMOS. And then T-rise, T-fall, I just set to 1 nanosecond, so it's super fast. And we're going to go ahead and do a time on. So when this thing is on, it's 5 volts. And what that really means is the switch is off. So our T on here is switch off because we'll have 5 volts. When the gate is at 5 volts of the PMOS, that means our system is off. And our period is going to be 100 milliseconds. So what that'll do is it'll give us 20 milliseconds with the switch on and 80 milliseconds with the switch off. Now, when we look at the formula here for our current, just to run some numbers, again, just to check our work and see how accurate the simulations are and to see how our spreadsheet action is. So our V system, our system voltage is 5 volts. Our inductor is 22 millihenries. That means that we will have a rate of change of 227 amps per second. But we're only going for 20 milliseconds as our on time. So according to the formula of the current, we are going to see about 4.54 amps at the peak before the switch is turned off. So let's go ahead and run this. Now you can see here it goes. So I gave me plenty of off time so I can see this thing completely turn off. But you can tell that it charges much faster than it discharges because it is only discharging through this sense resistor right here and this diode. And so when we look here, our peak current is about 4.49, which is pretty close to the 4.54 that we calculated. So we can see now that we have a rising edge and then a falling edge based on time of current through the inductor. So how is it that we can use this to our advantage? So at the end of the day, the total current that we're going to be able to pass if we went to a steady state in this circuit with the system at 5 volts is going to be basically 5 volts over our sense resistor, because at steady state at the end of the day, if we just leave the switch on, this inductor will become a short. And so our I max is just going to be equal to our voltage source divided by our sense resistor. Which means our max current can get up to 1600 amps. So this is all theoretical because you're more than likely not going to have an inductor on your board that has a saturation current or a capability of passing 1600 amps. But I'm using it for this because remember in the differential amplifier episode, we went ahead and set the differential amplifier to work with a 50 amp peak cutoff, right? Like that's what we were looking for. We were looking for the 50 amp marker, which was going to give us a 4 volts out. So in the same respect, we want to be able to turn this thing, we want to be able to turn this pulse on long enough to get us 50 amps. So we've got our little formula down here already set up. So because it's a spreadsheet, I can just go ahead and kind of mess with the numbers until I get to about 50 amps. So 225, close enough, 50.36 amps. So now if I just go in here and I'm going to need an off time of that amount of time. So it looks like we need about 3 times as much off as we do on. So if we need about 225, so we'll just call this 650 and milliseconds, and 650 minus 225 is going to be 425 milliseconds. So our off time will be 425, our on time will be about 225 to give us a total period of 650. And now let's go ahead, and then that's still under 1 second. So stop time 1 second, so our simulation is still good. So let's go ahead and run that. And we should see that we spike up to about 50 amps. So my time was a little off, about 47 amps. So it could have been a little bit longer. So we can see that's pretty good for just throwing some rough numbers out there. So we could either control current through this inductor, like let's say we want to have 50 amps. Then what we would want to do is try to keep this at 50, because we know that if we just have this switch on, our current will ramp up to 1600 amps, but we want this thing to hover at around 50 amps. So we need to be able to turn it on at 50 amps, but then what do we want to do? We want to be able to undo this switch for a certain amount of time, allow the inductor to discharge through the system, to self-discharge for a little bit, and then after it discharges for a little bit, we want it to go ahead and turn this switch back on so we can recharge that inductor. And so what we'll end up with is a sawtooth current waveform going through the inductor that peaks and dwells around with an average current of 50 amps in our output through that inductor. So how can we do that? So we know with our differential amplifier, we can monitor our sense resistor and look for 50 amps because we have that set up already. We've still got our sense resistor at 3 milliohms. we've got our RF at 20K, and we got our RN at 750 ohms. So we know that a differential amplifier will give us 4 volts on the output when we reach 50 amps. Now, we feed that into our comparator. As we know, this is a non-inverting comparator. So our V reference over here is 3 volts. I chose 3 volts because the peak voltage on this thing, you can choose anything that you want for the V reference. But if you remember from the data sheet, this LTC6244, it has a max VN on the input pins of 3.5 volts. So I was keeping my reference under that, so I have some headroom because I do want to add in some hysteresis. So now we have to think about is right now our differential amplifier is set up for 4 volts out, but that is no good for this comparator, since we know that the comparator itself has to have an input voltage on the pins of less than 3.5 volts. So we have to modify our differential amplifier a little bit so that our output voltage will max out at over 3 volts, just over 3 volts when we hit 50 amps, because we know that when we cross over the V reference point, that our comparator out will trigger. So we want our V out at 50 amps to be 3 volts or very close, just over that at a 50 amps. So we can go ahead and just change our sense resistor. And if we change our sense resistor to, let's say, 2.5 milliohms, it goes down to 3.36. So let's just go down a little bit more, 2.2. Okay, that's a little under 3, so we don't want that. 2.3. So 2.3 milliohms on our sense resistor will give us a load of at 50 amps with this RF and RN. So we can go ahead and change that over here. And set 3 milliohms. We want a 2.3 milliohms for our sense resistor. And that is all we have to change there. So now our differential output will output 3 volts for us when it sees 50 amps going across our sense resistor. And then our comparator, it is already set up with a reference of 3 volts. So as soon as we see 50 amps going through our inductor, going through that sense resistor, it'll have 3 volts on the output of the diff amp, and that'll feed into the comparator. And then the comparator, since our V plus is greater than our V reference, our N plus is greater than our N minus, that means our comparator out will go high. So how do we use it? Well, we go over here. We'll just remove this voltage source right here. Move him off to the side. And then we'll just take this comparator out. And we'll let the output of the comparator now control our MOSFET. So when this thing first turns on, what's going to happen? Our comparator out is going to be low because nothing is on. So our voltage at this pin will be low, lower than Vref. So our output will be low. And because it's low, that'll turn our MOSFET on. Our MOSFET on will begin to charge the inductor. Once that current gets up to 50 amps, our N plus pin will be greater than our N minus pin. And then our comparator out will then go high. And because our VCC on our comparator is 5 volts, and this particular op amp has rail-to-rail outputs, it'll output 5 volts to our MOSFET. The 5 volts to our MOSFET will turn the MOSFET off. Since the 5 volts is hitting the gate, our VGS is now 0. Switch goes off. And now the inductor will self-discharge. It'll self-discharge again until our current through our sense resistor is low enough to trigger the comparator to turn off, to go low, which means that our N plus is less than our V reference. Now, as such, if you remember also, we had set up the comparator to have some hysteresis. So we had some hysteresis here, and right now our trip point, our V reference, we've got that set for 3 volts because we changed that. with 20K on the RF and 1K on the RN. Our hysteresis is a total of 240 millivolts. And that means our upper trip point is 3.10 and our lower trip point is 2.86. So now we won't trip at actually 3 volts, we will trip at 3.1 volts. And so if you look over here, that means I will probably get to about 51 amps, 52 amps, something like that, a little bit over 50 because 50 is 3.069. So we need to go to 3.1, so we'll be a little bit over 50. And then we will let the system self-discharge until we see current through the system where the output is 2.86 volts. When the output goes to 2.86 volts of the differential output, then it'll trigger the comparator again, and it'll turn the system on. It'll set the comparator low, which will turn the system on, and then we will go through this cycle of charging and discharging this inductor where it is self-oscillating just through the differential amplifier, the comparator, and feeding back into this MOSFET. So let's go ahead and run this and see what it looks like. So you can see here we ramp up, and we're ramping up to just about 51.6 amps, and then we drop down to 47 amps before the differential amplifier gets below that threshold, and then re-triggers the comparator. So this is all happening by itself, and it's just being controlled by the comparator output. So if we look at the comparator output, you can see, and then we will zoom in to a couple pieces. So you can see the comparator goes up, goes into a self-discharge, drops down below the voltage level with our hysteresis. Output of the comparator goes down. Inductor can charge again until it hits the 50 amp marker. Comparator turns back on, and it just keeps continually repeating that cycle over and over again. And so this is a way we can current control an output for something like a motor or an LED or anything really that you want to current control. And you want to say, I want this current to go at this moment, because we could basically now mess with these formulas and we could do anything that we really wanted to. We can also clean up, if we wanted to, this high and this low value by just cleaning up this hysteresis. So if we wanted to make this a tighter triangle wave, right, we want to lower our hysteresis to something less than 240 millivolts to something like, let's say, 100 millivolts. So we just got to go in here and change some values. We can see that if we change that input resistor to 500 ohms, then our hysteresis becomes 120 millivolts instead of 240 millivolts, which tightens up our upper and lower trip points. So then if we change our RN to 500 ohms, and then we rerun that, we will see that this triangle wave becomes a lot tighter. And we can continue to manipulate this until we get a nice, clean, tolerable output current that we are satisfied with. So I hope you enjoyed this example of how to use a differential amplifier and a comparator to kind of self-control a circuit to allow a constant current output to your system for some purpose that you want to run. If you like the video, please like, subscribe, leave a comment down below, and share the video. And I'll see you next time. Thank you.